Next we have my friend Frieder Hochheim from Kino Flo. I'd like to give Frieder a lot of credit for all the investigations he's been doing, all the color science, and it's not just for his company, but he's very willing to share this information, and it really benefits the whole industry. So thank you, Frieder. Let's see what you have for us today.
Thank you very much. Today, this is a part of a very large presentation that I do, so I'm going to be talking fast because I have limited time, but I think it's important information for us to really consider. What I'm going to do is I'm going to start off with a clip. This was put together by Jeff Boyle. Many of you may know Jeff through CML. And what I want to point out now is here's a test that Jeff did using multiple cameras. There were two constants. One was a tungsten light. Cameras were all set to the tungsten setting, in other words, whatever the manufacturer recommended. And next to it was an LED, which he did not tell me which it was, but it's the same LED in each one of these shots. Also set to 3200. And so one of the things I want you to look for is how each of these cameras actually see tungsten, which is the one constant that we're all used to, and then see what happens on the LED side. So here goes. So that's tungsten, LED. Tungsten, LED. Tungsten, LED. Tungsten, LED. And remember, this is still the same LED, still the same tungsten. LED. LED. So what you start to see is these variances between how different cameras process tungsten. And part of that is due to the fact that we're talking about a D65 chip. These are all 6500 sensitive chips. And in order for it to respond in a warm environment, and by warm I mean anywhere between 3200 and when you actually read tungsten, tungsten is more like maybe 3000, 325. That's where these differences really start to stand out. So what I'm going to talk about in this brief presentation is an understanding of what spectral response differences are on the camera, and this sort of an illustration. I think we need to understand color gamut on various devices to sort of appreciate what's going on. Differences in white light spectrum. We need to understand the challenges of color matching between manufacturers of lighting, how to use gamut and XY in matching gel colors, and the use of camera profiles to account for differences in camera response. So when we think about it, we've been very fortunate over the history of the cinema to have constant light sources. We've got full spectrum light sources. We've had carbon arcs, tungsten, quartz, xenon, HMI, even the fluorescent, as much as it had a neon, had a mercury spike, has a much fuller spectrum than today's LEDs. So for the first time in our history, we're dealing with an inconsistent light source, and we're dealing with cameras that all have different response curves. So the perfect recipe for chaos. And when we think about tungsten days, Kodak embedded all the color science in the emulsion. All you had to do is expose it. Your cameras were mechanical. There was a constant. You could count on it. Yet we still did camera tests. And today, camera tests prior to production are something which are sadly lacking. So to understand what in fact is gamut. Now gamut refers to the entire range of colors that any one of these devices will be able to record, display, and play back. That's not just a camera, but a lighting instrument, projector, your laptop. So displayed there right now, that's Rec 709. So everything that falls within that triangle, you can reproduce. There are other gamuts that I'm sure you're all well aware of. So something like P3, which is a color space for digital projection. 2020, this is where we're now going to in terms of high-definition displays. They're starting to roll onto the market. Netflix has just said from now on, moving forward, we want to shoot everything in HDR. And then there's one other gamut that we should all be aware of, and that's the ACES gamut, and I'll explain that moving forward. Now, every camera, as I said, camera, display device, lighting instrument, they all have gamuts. Yet you will not see a camera gamut displayed from a manufacturer. If you go online today and look for camera gamuts, you will see that there's most probably a lot of articles that say there is no such thing. There is no such thing as long as you don't have the data. So we've modeled about 16 cinema cameras, and of the 4 that we have displayed here, I'll show you what those gamuts look like. Now remember, this does not make a camera better or worse, but these are differences in these cameras. So there's 709, and there it goes. So this is one camera, the next. So you can see right there the differences in how these various cameras see light and what they're also capable of recording. So one of the cameras can see very down into the lower right section of the CIE color space chart. So it's actually picking up some very, very deep reds. Now the irony of all this, of course, is the camera is capable of recording all this information, yet if your post flow isn't in 709, you're right back into that little green triangle that we're looking at. So yes, you can record it. Yes, a director can maybe see that on the set. And now you have possibly an unattainable expectation. So if a director falls in love with, say, a saturated color, and you go into 709 and you can't reproduce it, who's the boo-boo, right? So this is where we need to have an understanding of the technology. Kodak film, Fujifilm, they also had gamuts. We never thought of it in those days as gamut because it was photochemical. But having modeled motion picture film, just out of curiosity, I said, what would that look like? So there's a tungsten film and daylight film, the blue line. So what's interesting here is that you see the difference, the offset between the tungsten perimeter near the border of 2020, and you see that gap between 709. And so when we remaster movies that were obviously had colors that could be seen as projected, but could never be displayed in 709, now when we go to 2020 and remaster for 2020, we're going to have that experience of what it was like watching that movie in the cinema. So there's a real sort of benefit for going in that direction as the technology pertains. So ACES, this is called the Academy Color Encoding System, and this was defined by the Academy of Motion Picture Arts and Sciences, and it was a means of trying to create a digital negative. How do you hold digital negative in the digital world when it's a bunch of series of zeros and ones? With celluloid, obviously, we had a stable mechanical base that could hold all the information. So what do we do now in today's day and age? So the idea was to create a space, a gamut, that would cover the entire visible field. And this is not even knowing where our technology is going, but we figured if the eye can see it, let's at least capture that. So what we have is, we call this a digital source master. So the camera raw information comes into ACES. The camera manufacturers supply a CTL, or a color transform language, and that then outputs it into whatever format you now want to work in. If you want to work in 709, it'll output it in 709. If you want to work in 2020, it'll output it in 2020. So the theory here is that once you've outputted your movie and you've timed it and everything else, you can store all that information within ACES, and 20 years from now, a technology comes along that is different from what we're doing now. Instead of completely remastering these movies that were done previously, simply applying a new CTL will allow those transform codes, they'll allow you to rewrite that older data into the new format. So that's the theory. It's in the works. It's still being modified. Some people like it, some people don't. It's still sort of a mixed response. But for the most part, I think this is absolutely a positive direction to be going in. When we talk about gamuts, Kino Flo has a gamut. Sort of looks like that. 709, P3, 2020. And you can see how there are obviously certain colors that are not within the gamut of the Kino Flo to reproduce. What's important, though, is that what's in the middle is the white, and this is where we're all about the white. So first and foremost, it's about capturing a full spectrum white, because that's what's reflecting back to the camera. All the real world objects, whatever they are, That's what we're really focusing on, trying to get back onto the camera. The bonus is all colors on the periphery. So if you want a saturated color, the units have a capability of reproducing that. So now, as a manufacturer, you have to think, what's the goal here? What are we trying to do? So the gamut is established by the primary color points that we choose. So what we have is we have a white light engine, 2 full spectrum whites. One's a warm tone, one's a daylight tone. And after that, we use RGBs to actually, as we blend these 2 whites together, we use the RGBs to track the blanking curve, or we track actually the camera response, since we've actually recorded the camera response. Now, if I was a manufacturer and my goal would be to reproduce more colors outside of that spectrum, say gel colors, then I would add other LED elements that would help me expand that gamut. And so that would be possible to, using additive color mixing, try to reach out to some of those colors that possibly were not capable in a smaller gamut. But remember, still, all of this comes down to your workflow gamut. So yes, you can generate certain colors. Keep in mind, what is your workflow? If you're in 709, whatever saturated color you have out there is still going to be restricted by the 709 gamut. So what does that mean? It means you'll still have the same hue angle, but at a lower saturation. And this is where conflict possibly with directors come in, where you've given them a nice cherry red color, and it comes to trying to reproduce it in 709, and it's just not there. It's coming as a much paler color. In the middle is the white. This white light full spectrum is common to all the gamuts. So every gamut starts off with a D65 point. And so that's how we define the starting point of a gamut. Full spectrum light, that's where your skin tone reproductions come through. This is where the other objects that you're illuminating, you're doing a commercial, you've got corporate colors, you've got packaging that has to be accurate. This is where the white engine comes into play. If you're not dealing with a full spectrum white and a somewhat diminished white, then it really comes down to the spectral distribution of that white. Is it capable of capturing those colors and reflecting them back? Now, it's possible to produce colors that are outside the gamut of, let's say, an instrument that is not a broader gamut. And so instead of using additive, where we can't reach out to that color point, you can actually use a subtractive methodology, which is what gels are. They're a subtractive method of generating light. So by putting the gel on the white, be it either 32 or daylight, now you can reach out to that color point, and you can realize that saturation. So that means that the gel is letting through only that wavelength. In this case, it's a yellow, only letting that wavelength through and cutting out everything else. Of course, you end up with a little light loss, just like we had in the good old days with tungsten. So bottom line is, gels still serve a purpose. As long as you've got a nice full spectrum white, you'll be able to realize those colors. Now, just to illustrate this a little further, at AFI, there was the cinematography fellows are required to generate a lookbook, meaning, what is this picture supposed to look like? So they'll use photographs, they'll use color swatches, they'll do sort of a display of what kind of a look this picture is going to have. And so the director is brought in on this, the cinematographer, art department, makeup, wardrobe, very important for wardrobe to be on it. And in this particular case, they were trying to reproduce, one of the themes was the Storaro yellow, which is very similar to Lee 101. So they went ahead and did camera tests, just like we did in the old days. So tungsten light, they measured it at 2900. They set the camera to 2900. They put the gel on it, and that's a gel on tungsten. So they said, okay, we also want to work with LEDs. So let's dial in the LED to 2900. That's what our tungsten source was. Let's throw the gel on that. Great. So, okay, so now let's use additive color mixing. Let's just, within the fixture that we have, take the green and the red. Let's just combine those two, and the camera's still set at 2900, and this is what came out. And they went, oh my God, something's completely off. Because they were using a desk, maybe there was a miscalculation of data going to the desk. So they cut out the desk, and they looked at it now just in its raw form, trying to manipulate it. Now the eye would see this as a yellow, but the camera was not seeing it as yellow. So what's going on? Bottom line is they didn't have time to figure it out. They came to the ASC Technology Committee and asked what went wrong here. And we determined that, in fact, this is a situation where you have a D65 chip on a camera. And when you dial that into 2900 response, it was not within the resolution of that camera to perceive that particular wavelength of color that was being generated additively. You want to find this out in pre-production, not on the day of shooting, because you'll be royally screwed. So in this case, they did just that. They did not do additive color mixing for this particular case. They went with the tungstens in gel, and they went with the LEDs in gel, and it was a successful shoot. So in order to just prove the fact that this was a sensor issue, I simply dialed the camera to D65, and there was the yellow. Somewhat desaturated, just like we would expect it to be. So again, these are things which we need to be aware of as we're shooting, and we all get sort of carried away with colors and whatnot. There are issues that are going to bite us, and unless we do the camera testing up front, there's no way of really knowing. Now, there's one other gamut that I think is important for cinematographers to think about, and that's what the reflected light coming up, or what the white light engine represents. And so there's a guy named Michael Pointer, who was a Kodak engineer, and he came up with Pointer's gamut. Now, these are the colors if illuminated by daylight, for example, and they're falling on objects that are predominantly matte. They would reflect back in this manner. So what we see is that certain colors, certain saturated colors, will fall outside of 709, but for the most part, the camera gamuts that I showed earlier would encompass all of that. So again, these are considered real-world colors. This is what reflects back. And this is why having a full spectrum white is so important, especially when you're trying to reproduce skin tones or doing commercials and getting the colors right on packaging and corporate colors and that kind of thing. There are other ways of generating or trying to come up with color gels. We just have to think about every color space is defined through mathematical points. So they either do it by percentage in values of 100, or in percentage, or in 255 increments. So 255 increments refers to essentially the number of increments that you'll find on a DMX board. And so in this case, this is an app from Show Tool Swatch, and they give you values in either percentages or 255 increments. So in this case, that's sort of a representation of where the color point would be. Now, if a color point falls outside of that, this app will actually show you, or will actually give you a value. Now, it's also important to remember that where we talked about gamut, this app is a 709 gamut. And this is where it gets interesting. If you simply take these numbers and plug them into multiple fixtures that are from different manufacturers, if they're not on 709 and they're on their own gamut, which is established by whatever color points they choose to work with, these things are never going to match up between manufacturers. So this is something that when we're struggling to match between fixtures, you really need to understand what the gamut of the instrument is, and the manufacturers have to give you that option of actually dialing in the gamut. Otherwise, you're just chasing your tail. You're never going to get these to match. So the value that it gives you will actually be the value on that crossover point, not where it actually would be lying. Lead gels, they also have a great app. Now they're taking a slightly different approach, and they're using XY coordinates. And this is a way of avoiding the issue of gamut altogether. The only thing to note there is they're replicating a gel on two different light sources. So source C is daylight, tungsten, obviously what that is. So those are the same color points, but defined as an XY. And now in the case, if you have a color point that falls outside of the gamut, this app will show you where that is. Now, it's still dependent on the gamut of the instrument you're working with. Can it actually reproduce that? And if you have XY, you may be able to enter that, but if the gamut of that fixture can't handle that color point, it's still going to reproduce the color somewhat inaccurately. It's complicated. ESTA also known as Plaza, is proposing that we come up with a color space that is big enough that should encompass all the different LEDs that are currently on the market. And so what they did is they used the Kodak Pro Photo color space. And now remember, all gamuts are always defined in D65, except this particular one. They've actually chosen tungsten. So that creates a problem. We've now joined that committee at ESTA, and I think it's going to go moving back to D65. The other thought is, well, maybe we'll just move everything to XY and eliminate the whole gamut idea. But as an industry, we're urging manufacturers to give you these gamut choices. And the theory being very simply that if we all choose to map our color within a common gamut, the color profiles, that information, when that profile goes to a desk, your board operator will in all likelihood be able to match up your colors better than what we currently have, which is a hodgepodge of open gamuts. God only knows where these gamuts are, and the likelihood of them matching up is pretty much zippo. Just to show you a quick idea of an example of how this would work. What I have here is a representation of, this is a mauve. Again, it doesn't matter which manufacturer, but I'm going to take this into a color space mode. And so that's the Kino Flo default. That's Rec 709. P3, 2020. And ESTA, that uses a different white point. It uses a tungsten point. So this gets confusing. So one of the reasons we're urging to stay away, keep everything, all the gamuts that we work with in camera and everything else are always D65. There's no reason to wander off the point. So I think that's ultimately going to change. So our Kino Flo default, 709, P3, 2020. So you really see how some of these differences play into and I'm running out of time. Life in the fast lane. I'll cut to the chase. One other thing that we've done, because of all these issues, we talked about that first clip that you saw where the cameras were seeing things differently. So by profiling the cameras, we've now introduced the ability to actually dial in a camera. So we have the Alexa, we have the Panasonic, we have the Sony Vericam, and the DXL. So just as an example of how that would look, our native color was the Alexa with a fudge factor for Sony and Panasonic. But now, this would be the difference between Sony Venice, Panavision, Panasonic. Alexa, Sony, Panavision, Panasonic. Arri, Sony, Panavision, Panasonic. So this is trying to address that issue that we saw in the beginning, where even tungsten was being viewed differently, and you saw how dramatically different some of the LEDs were. So this is a complex issue that is not going to go away. All of us manufacturers are dealing with these issues, and this is how we've chosen to try and tackle it. So thank you for your patience, and stay tuned.